Hey,
Hi.
how are you?
Oh, I don't think you can hear me.
I can hear you.
Can you hear me?
Yep.
Oh, I can't hear you then. Hold on. Wait.
Mm-hmm.
Okay,
All right, you can
now
hear
I
me?
can hear you.
All right. So, let's get right to it.
All right.
All right. Yeah, what do you want to start on?
Chem Physics.
The section bank?
Mm-hmm.
Okay, which number?
Um, I'll tell you right now.
Mm-hmm.
Number 15.
Okay. Oh, we did this last time.
Did we do 15?
That's the finding the minimum resistance.
Oh yeah, that's true. That is true. And then we did the separation, so then the next one will be 16.
Yeah, we did that also with the decibels.
Mm, I don't. Okay, yeah, it was 10 to the 5. I don't have the answers here. That's why.
Mm-hmm.
Okay, so yeah, we did it. Okay, yeah, so we stopped here at circuits, and you said that you didn't want to do this one because it was too complicated.
Yeah, this is a Wheatstone bridge. I mean, I could show you how to do it, but it's like on the hard side for what they ask you on the MCAT.
Mm-hmm.
So we don't we can focus on other things, I would say.
Okay. So there is another passage. Oh, we did this one too. Uh, okay, so then this is weird how it doesn't give me the numbers for the questions, but I guess the second one from passage 3, which says, why did the liposomes fluoresce during size
Mm-hmm.
exclusion?
It should be on the top left, maybe like 19
It
out of
says like
100.
no, because it tells me like based on how many I have left that I haven't answered.
I see.
So
Okay.
because I have answered some of them, it says 5
Mm-hmm.
of 86 right now.
Got it. Okay.
Yeah.
So let's see. So why do the liposomes fluoresce during size exclusion chromatography? Um, so we're gonna have to look at the passage here. So basically, what's happening in the passage? They're basically saying that compound one. They want to see the effect of pH and compound one concentration on the formation of liposomes. And then they say what liposomes are. They're basically spherical versions of like a lipid bilayer. So compound
Mm-hmm.
one, we see it looks like a phospholipid of some sort. You see that in compound one?
Yeah.
All right.
Mm-hmm.
Now so they made liposomes using 1 ml of different concentrations of compound 1, ranging from zero point zero 0.05 to zero point 0.2.
Mm-hmm.
And by the way, like, tell me what those are in fractions. What the zero point 0.2, what is that as a fraction?
1/5.
Good. What about zero point
Okay.
zero 0.05?
Uh, 1/1/10? No, 1/20.
Good. Good job. Awesome. All right. Good. Good. Good.
Okay.
All right. At pH,
Yay! I'm getting
yeah.
better at fractions.
Yep. Yep. All right. At pH 7 by ultrasonication and agitation in the presence of fluorescent dye that emitted light at 520 nanometers when excited at 460 nanometers. Um, so that's kind of interesting that it absorbs light at 460 nanometers, and it causes an electron to get excited, and then when it goes back down to the ground state, instead of emitting a photon at the same same wavelength,
Wavelength.
it emits one at a longer wavelength. So that tells you that some energy is lost in this process.
Okay, hold on. Some energy will be lost because it's emitting light at a higher wave at
A longer
higher
wavelength.
wavelength, which means lower energy.
Yep.
Okay.
Good. All right. An aliquot of the liposomal suspension was subjected to size exclusion chromatography, and the results are shown in Figure 1. Further aliquots of the liposomal suspensions of compound 1 had their pH adjusted from 2 to 12. Results from size exclusion chromatography indicated no changes occurred. So okay.
I'm sorry, what is an aliquot?
It's just I guess it's just what they call the liposome mixture that they put like compound 1 in.
Okay.
And it's what comes out of the size exclusion chromatography. I just think of it as like a little container thing of like sample. Yeah.
Further aliquots of the liposomal suspensions of compound 1 have the pH adjusted. Okay. Okay, let's keep on.
Yeah. So Figure 1, you basically see elution volume versus fluorescent intensity, and so you see that like as the concentration of compound 1 decreases, you have a greater elution volume, but a lower fluorescent intensity, right? Okay, so when we look at that, we just have to like see like what it means, and that's basically what it's telling us. Okay.
Is it? I am not really like understanding the actual experimental setup. I mean, I understand the graph and I understand the relationships between how elution volume and fluorescence intensity and all the concentrations, but what is it that they're trying to do, more or less?
So.
Or is not important?
So Figure 1 is just, so they're basically just, sorry.
That's okay.
Scam Lactate. All right. So basically they're making liposomes using 1 milliliter of compound 1 at various concentrations, and they're putting it in size exclusion chromatography just for some reason, I guess. Later on, they want to see the effect of pH on these like aliquots of liposomal suspensions, but results are saying that there's no changes.
Why there's Oh, sorry. Results from size exclusion chromatography indicated no changes. How is the fluorescence intensity related to the pH
it just
change?
So they're basically, all right. You know what? This is a good time for me to write down like how to go about like a passage. So here, I'll write it down. All right, you can see my screen?
Yes.
All right, so let's see, passage 3. Um, so I think I'll use Microsoft Whiteboard and then end up copying and pasting things into the OneNote because it's just a lot faster. Like
Okay.
like for instance,
Yeah, as long as you share your screen, it doesn't really matter where you.
yeah, because I already drew things in my OneNote and it hasn't even updated here. But right here, I'm gonna draw something on the white. Yeah, there. It finally appeared after like 45 seconds. But on the
All right.
whiteboard, I'm gonna draw something right now. Instant.
Okay.
Okay.
Perfect. Is that like that comes with Zoom, right?
Oh no,
Or no,
it's
it's
like
different.
with Microsoft Whiteboard, but I would at the end just do screenshots and put it into your notebook.
Okay.
So okay, so passage 3. Okay, so basically what they're trying to find is the effect of pH. Okay, so like effect of pH and compound 1 on liposome formation. So
how does pH affect the formation of liposomes using compound 1, pretty much, right?
they want to check. They want to check like what each of these do. So that's why they have like an experiment with just different concentrations of compound 1, and an experiment where they adjusted the pH as well. And for the so when they just used compound 1 and didn't change the pH, they found that um, they found that basically, I guess, larger versions, I guess, like they basically just, okay, so I'll just say like compound 1 they found was inversely proportional to or rather the concentration of compound 1 is inversely proportional to elution volume.
Mm-hmm.
And when they did it with pH, there were no real changes. So this didn't change anything. So that's how I would write it. So yeah, when I look at passages, I write in like a type of like shorthand like this with arrows and things like that.
See, so
Mm-hmm.
figure 1 says, like the text below, it says elution profile for liposomes generated from compound 1.
Mm-hmm.
Never mind, at different concentrations.
Mm-hmm.
Because I was like, how would you know that this is relating to
Mm-hmm.
it says result. So they did size exclusion chromatography for both different concentrations and different pHs, right?
Yeah.
Okay. And then they're only showing the graph for the different concentrations because there were no changes occurring with changing pHs.
Yeah.
Now, my question was, how is fluorescence intensity related to all of this?
Oh, fluorescence intensity just tells you that that the compound 1 is there because they put compound 1, like, because how else are you going to know that um, that like your elution volume is like zero point 0.2 millimolar? Like, how are you going to know that? How are you going to basically know the concentration of compound 1?
Right, you know the relative differences between the volumes, but you don't know the exact concentrations if you didn't add the fluorescent intensity, right? The fluorescent dye.
Correct.
I
Yeah.
mean, you would be able to see the peaks, I guess.
Um,
No.
If you didn't add
Not
the
really.
dye, then you wouldn't be able to see any fluorescence, and you wouldn't be able to tell if you wouldn't be able to tell what concentration of compound 1 there is, if
Okay.
any. So that's what the fluorescent dye is for.
Mm-hmm.
Okay. Then let's see. Well, okay. I mean, I can answer the question now, but I'm just going to look at that last paragraph.
Okay.
Liposomes generated from compound 2, which is oleic acid, aka olive oil, gave similar results to those shown in figure 1 only at pH 8.5. So, compound 2 is basically like compound 1 only at a pH of 8.5. At pH of 10 or above and 7 and below. So, liposomes did not form. So, maybe I'll do something like this. Like, compound 2 did not form liposomes at pH less than 7 and pH greater than 10. All right, and then they. All right, we could just answer the question now before going on to the rest of it.
Like I just want to answer the question.
Yeah, because it's like I said about like working memory. You don't want to put too much in your brain that you don't need. So let's look at the question. So they're saying, why did liposomes fluoresce during size exclusion chromatography? So
I would just go by C, and not because I know like just because of what you mentioned or what we read about the fluorescent dye emitting light at a different wavelength than what it was actually absorbing an
But
electron. But
C is talking about intermolecular interactions.
okay.
So that would be between molecules. And they're saying that would lower the energy of the excited state.
How is that wrong that it's between molecules?
Oh,
I mean,
because
there's several molecules of compound 1, aren't they?
But so when an atom absorbs a photon, and it like excites the electron from a ground state to an excited state, that happens to the atom itself. Like, it doesn't really matter what the environment of the atom is in. And intermolecular interactions, which are between molecules, don't really affect it. It's because it's happening within within the atom itself.
Okay. Would
So
intramolecular interactions affect that?
no, nothing will affect it unless you're like blocking it with like, I don't know, like titanium or I don't know, tungsten or something like that. But so
Okay, so it's definitely not C. Fluorescent dye was trapped inside. That emitted. Wait. I don't know why would fluorescent dye be trapped inside if. I mean, I know that a liposome is used for that, but it sounds very stupid to like just say, oh, because the fluorescent dye is trapped inside, then it's going to fluoresce.
Hey, give me like a couple of minutes. I just have to show my apartment to someone.
Yeah, don't worry.
Okay, so I was drawing like the beginning of a liposome here, and
Mhm.
like so I mean so they're saying that it's in the presence of a fluorescent dye, and if you want that dye to tell you how many liposomes are being made, you do want it to be trapped inside.
Right. So I was thinking if it says exclusion chromatography, you need, because you're going to be like sorted out based on size, you need a way to keep track of it
Mm-hmm.
regardless of the size or regardless of the amount of liposomes. So I believe like the only way would be they're trapped inside.
Yep. Yes.
But that's something that I found out after I actually looked up size exclusion chromatography.
Oh yeah, you don't even need to know size exclusion chromatography, because like all it's kind of saying is like if the liposome wasn't all right. So you see where I drew like the dye inside. Like let's say the dye was
Mm-hmm.
outside, right?
Mm-hmm.
Then that doesn't tell us anything about how many like liposomes are being made, right?
Right.
So it would have to be trapped inside in order for it to be something that tells us how many liposomes are made.
Right, but isn't the question asking? So I thought more of the question as like, what is it or what feature of this experimental setup it's actually making the liposomes fluoresce?
Mm-hmm.
Like I was thinking more of like, why are the liposomes fluorescing when we're using this dye?
Why did
No?
liposomes fluoresce? Think about it. So it's asking not why did the fluorescent dye fluoresce, but it's asking why do the liposomes fluoresce, right?
Mm-hmm.
And liposomes don't fluoresce on their own, right? So if a
Mm-hmm.
liposome is fluorescing, it must have that fluorescent dye inside of it.
Okay. How about light reflects from the surface of the sphere?
Um, like that, it wouldn't be the same as fluorescing. Like light could possibly reflect from the surface of a liposome. I mean, uh, but they're asking for fluorescing, like specifically at 520 nanometers. So,
Mm-hmm.
and they talk about it, being done in the fluorescent dye, and so so um so okay, so like it could reflect light, sure, but they're asking why does it fluoresce? And when they say fluoresce, that means like it's giving off like I think like green light or blue light or something like that at a specific wavelength of 520 nanometers.
Okay.
Yeah, the dye gives off um, light at 520 nanometers, and let's say the liposome, like I don't know if it's like oil or something, like gives off like a rainbow or something like that. But the dye itself gives it off at 520, and that's what you're measuring. So
So light reflects from so then the whole reflection thing will be from the actual liposome? Is that what you're trying to say?
what's that? The reflection? Like
Yeah.
liposome could reflect some light. I mean, sure, but they're asking specifically for fluorescence. So the real question is just asking why do the liposomes fluoresce? During size occlusion chromatography is just some extra information, and you don't need to really know that to answer it. But all you need to know is that we're making liposomes, we're using a fluorescent dye, we mix the two, and now we have liposomes that fluoresce. So how can a liposome fluoresce? Only way that can happen is if the fluorescent dye went inside of the liposome and did what it does.
And why did they put the macromolecule, the extensive conjugation of the macromolecule?
So that's like if you're asking about the fluorescent dye itself. like fluorescent like
Oh, I thought they were referring to compound 1 though.
Yeah, like they're that's just that's just an answer choice. That would be the answer if they asked why does the fluorescent dye fluoresce? Because things that fluoresce or give off color have a lot of conjugated double bonds. So that would
So by
answer.
macromolecule, they're not referring to compound 1, they're referring to the fluorescent dye.
No. Like, if they were referring to the fluorescent dye, then it would be the correct answer. But they're just saying they're not really telling us anything about what macromolecule they're talking about, and it doesn't really explain why the liposomes are fluorescing. But that's just like a choice that if you thought they were asking why did the fluorescent dye fluoresce, because that kind of thing works from conjugation. Like here's for example like a pigment like melanin, like like for like dark skin, it looks like this. And you see how there's you remember conjugated like pi double bonds?
Yeah.
It's like like a double bond, single bond, double bond. And see how there's extensive conjugation here?
Right, like resonance, I guess.
Kinda, but like specifically conjugation, which is conjugated double bond. So they look like that, like a double bond, single bond, double bond. And these give off light, basically. So that's why like pigments and things have extensive conjugation. Right?
Why would they? This is just like out of topic, but would they give off light just because of the fact that electrons are moving throughout the double bonds, or?
Yeah.
Okay.
Yeah, it's funny. When I did a little bit of scribing, there was a patient who was on something called azo for UTI. And,
right.
Yeah, and when we collected the urine sample, she was like crying because it was red and she thought that it was blood. Why did I take urine?
Right.
And I remember I was being like, I was just telling her like that's because azo has conjugation, extensive conjugation, so it's just giving off that reddish color. It's not like blood. And I remember getting in trouble for that because they were like, we don't have time for you to like explain everything and things like that. And I was like,
no way, you actually got in trouble for it?
Yeah.
Well, she was probably like, what the hell are you talking about? We always tell patients like, oh, azo is gonna make your urine orange or red.
Yeah.
But then they're like, okay, yeah, whatever. But I never thought it was because of that.
Oh yeah. Just like when someone was asking me, like when you check some pulse oximeter on their finger, how that works. And I was just like, yeah, because it gives off like a laser. Like same thing with like my Fitbit. You see how there's like a laser?
Right.
So it basically like can use that to see like how your blood is moving in your capillaries and stuff. But the place that I worked at, they were just like real assholes about like time, and they just want
what an asshole.
They just want you to get them in and out at the same, and also like I didn't like follow like the shorthand that they wanted me to, because I can type super fast and get a lot more information in.
You could what? I'm sorry.
Oh, like type really fast, so I can get all the information in and more without having to follow like their whatever shorthand.
And they didn't like that you were fast, I guess? Or they didn't like that you had so much time off to go and explain people why azo was thinking of urine orange.
Yeah.
So they're like, he needs to be busier.
Yeah. It was crazy because I remember for the interview, they had us do like typing tests, and everyone at the interview, like they couldn't, I think the minimum was like something really low, like 40 or 60, I think. And they just couldn't do it, and everyone at the interview they kept doing like it over and over and over and over again, and I was like just really fast like from the beginning and left. But I got in trouble because
Do
my
you
phone
use like
kept
all
going
of your
off.
fingers, or were you taught to do it with all your fingers? Because I am
No,
a
the thing
fast
is,
typer,
like,
but I only use these two
oh
fingers.
yeah, that's what I, yeah. No, that's what I do. I was never taught typing, so I don't know, like, I don't do the home keys thing. And I mostly
Mm-hmm.
type with these fingers as well. But I've
Yeah.
been like using a computer like hardcore since like I could remember, since I was like 11 and stuff. So I just like, yeah, I guess like just,
Cool.
yeah. um so okay, so anyway, does it make sense that it's because the fluorescent dye is trapped inside? Because you're asking about the
Yes.
liposome, which doesn't fluoresce on its own. But yeah, A, it would be the answer if they asked why does the fluorescent dye fluoresce? And yeah,
Mm-hmm.
things like that are like, with conjugated double bonds and stuff. Okay. Um,
That's cool. I didn't know that.
mm-hmm.
That's really cool.
Yep.
Okay, so then it will be B.
Mm-hmm.
All right, so what does the behavior of liposomes prepared from compound 1 and 2 upon mixing indicate about the energetics of their transformations?
Yeah, this one I thought was pretty hard because I know about kinetic control and thermodynamic control, but I remember getting this one wrong because I wasn't able to use what I knew about those definitions and apply it to this. Because
Mm-hmm.
generally speaking, like kinetic control is a measure of how fast something is made, and thermodynamic control is a measure of how stable that thing is that's made.
The product is how stable the product is?
Mm-hmm. Yeah.
Okay.
And like, okay, let's see. So compound two, and now I'll read like the last part of like the passage. So they mixed liposomes of different sizes, and observed that those formed from compound one were uh, stable to mixing, but mixing those from compound two formed new lysosomes with an average size expected for the effective final lipid concentration. So they're saying that um, when they took the different things for the different liposome sizes, or liposomes of different sizes for compound one that formed, like whatever the point 0.2, 0.15, all those ones, when they mixed them
Mm-hmm.
all, the the liposomes retained their size. Like they were like a mixture of different sized liposomes. However, when they mixed the ones from with compound 2 involved, the liposomes, instead of retaining their sizes, they combined to make a new liposome that has a size that is kind of like equivalent to like the total lipid concentration. So like if they added
And
up, yeah.
so it was like a mean of the total lipid concentration, or
Yeah, like it would be equivalent to that. So like so basically like what we have here, so like let's see, compound 1 and compound 2, when they mixed it, you have like, liposome of this size, of this size, of this size, of that size, of that
oh
size.
wait, can you scroll
Oh
down
yeah,
a little
whoops.
bit?
Yeah.
Thank you.
So of that, but for compound 2, they just mixed and formed like one new liposome, I guess, that is equivalent to like the sizes of these combined, or like the average of those, combined. So like I suppose um, like for this, like I'm guessing like this would be the one for the for compound 2, and that is equivalent, like this amplitude is like equivalent to like this plus this plus this plus this. So
Mm-hmm.
like okay, like compound 1, if you mix them all, you're going to get some of this, some of that, some of that, and some of that. Now let's just
Right.
say for compound 2, these guys mix with each other to form one that's like that.
Okay.
So yeah, if you like mixed all these and made it so it formed one liposome, it would look like this. I mean, probably larger. So, yeah, and it says that like here, like they mix liposomes of different sizes, and those formed from compound 1 were stable to mixing, meaning that like this formed from compound 1, this formed from compound 1, this formed from compound 1, and when mixed, they're stable, as in they retain, their sizes.
Their original, yeah.
Mm-hmm. And then, but mixing from compound 2 formed new liposomes with an average size expected for the effective final lipid concentration. And like this is kind of like that. So a new liposome is formed with, that kind of like size.
Is it C?
That's what I put also. But
Okay.
it's B. And the reason for that, like, it makes sense to me now, is because, like, this is ultimately... So, like, let's say you did it in a hurry, which is a kinetic thing, you'll get things like that, right? But these are not the most stable. It's the most stable if they completely mix with each other to form, like, one that's like that.
Mm-hmm.
So, yeah, this is, more stable. And this over here is more, like, fast.
I mean, I wouldn't think so, because if you have already, like, the compounds, the liposomes that were formed from compound 1, they're already formed. And then you mix them, and they still can keep their original form, then I would say that they are under thermodynamic control, just because the product is more stable.
So, like, if you're mixing them, right, and they retained their original sizes, nothing changes in terms of stability. Because they still are just, their same sizes. They just happen to be next to each other now in the mixture. Whereas this, because this comes from something like this with, different sizes. But this forms like one larger thing. It's kind of like, almost like the reverse of what, like, bile does.
The reverse of what?
What bile?
Like actual bile from, like, the gallbladder?
Mm-hmm. Yeah, it's
Okay.
stored in the gallbladder, but where is it made?
Liver?
Yeah, good.
No.
Yep, liver. And
Okay.
and it works as a detergent, which emulsifies fats.
Mm-hmm.
So here, I'll just do like an aside here. So like, let's say this is like, a big like fat, and whatever, bile comes in and it emulsifies it. Basically, it breaks it down into smaller, like, liposomes called micelles.
Mm-hmm.
And this means that it can get solvated much easier because you're making the surface area a lot higher.
Less. Oh, wait. The ratio of the volume to surface area much higher?
Well, I mean, the volume decreases, but just the surface area increases. So it's easier for this to be broken down.
Mm-hmm.
That's like for everything, right? Like like a cube of sugar versus powdered sugar. Like, the powdered sugar is going to be solvated. It's going to be like, it has greater surface area, so the solvent, like coffee or water or whatever, gets to hit it from all sides if it's like in powdered form. Whereas if it's like a cube, there's a finite amount that the water can solvate it.
Okay.
So yeah, so that's what bile does. And this is kind of like the reverse of that, where it comes from something like this, and it mixes to form a new thing like this that's more stable. Because this is more stable than this. Because
Right.
this gets like digested and broken down and stuff.
And you said kinetic control was the stability of the actual.
So anytime we're talking about kinetics, we're not dealing with anything regarding stability. Like, here's another example. So, for like a chemical reaction, right? Like, we have like the energy level of like the reactants here, right? And then like activation energy, right? And then products there.
Mm-hmm.
Whoops. So okay. Now, let's see. So the energy difference between the reactants and the products, that is a thermodynamic quantity, because it's simply the stability, like energy level, like stability of like the reactant compared to the stability of the product. And that's a thermodynamic thing. However, this activation energy thing, right?
It's a kinetic quantity.
Yeah, because like, when you add a catalyst, it lowers the activation energy, right?
Mm-hmm.
Which makes it go faster, makes the reaction go faster. Like a catalyst, right?
I'm just like processing through. So, is kinetic control referring more to? I mean, so why would they say control? I guess it's just a quantity, or it's just like a discrete value, or like a certain value that you need to.
So okay, check this out. So activation energy, if you lower it, right? So okay, activation energy, if lowered by a catalyst, makes the reaction faster.
Go faster.
But the stability,
is the same.
Yeah, is not affected, because the reactant will still have this, energy level, which corresponds to its stability, and the product has that energy level, so that's not changed. So this is a matter of thermodynamics, whereas this is simply a matter of kinetics, because it doesn't change the stability of either reactant or product.
I have a love-hate relationship with thermodynamics.
Oh yeah.
Because I've put like so much time into it, and whenever I think I get it, it's like, oh no, I didn't get it. But
I remember
now that I'm understanding what you're saying, is the activation energy, why does the activation energy is there? Do you need it just to make the reactants
so
collide into the product, or like the molecules of the reactants collide into the product? But why would you need higher energy if the energy of the products is less?
So it's like, okay, if it was not like a hump that it has to go through, then you wouldn't have reactants or products, right? Like, let's say it looked like this. reactants energy is up here, products is down there. If it was this without the hump, then there wouldn't be any reactants in existence.
Because everything will turn into products.
Yeah, because it's just going down.
Mm-hmm.
So
okay.
Yeah, so this hump is what makes reactants and products exist. And like mostly all of like the chemical reactions that happen in our bodies would not happen. It would take like millions of years for them to happen if not for catalysts, aka enzymes.
Correct.
So that's why you have that hump there. It's like, I don't know. Yeah. So yeah.
It's kind of like a lock that it's put there on purpose so that there's a separation between reactants and products. Okay.
Yeah. And like, the in-between part is going to be like the highest energy because nothing exists in that in-between part.
Do you mind going? I know we're like deviating from the question, but
Sure.
like now that you're explaining that, do you mind going over like I don't know how, if maybe the way that you would explain it would sound better to me, but like I memorized like when it's going to be like a spontaneous reaction, non-spontaneous, or like when it's negative delta G and blah blah blah. But based on that, like you can tell without memorizing the formulas. Is that possible?
You were saying you're saying
like to know if a reaction is going to be like to kind of estimate the delta G of a reaction, or if it's endergonic, exergonic, and
I mean, you would need like like the bond energy stuff, enthalpy, temperature, entropy, things like that. Here's like another graph of like, so this is for like an SN2 reaction. There's that transition state. So that's what you're usually seeing. So like for instance here, this is the reactant, right? And it interacts with this nucleophile, and you have this transition state in between, and that's, a peak in terms of energy, meaning that it's not stable here. And then it reaches, the product here. Now, that's what that hump represents, a transition state where it's in between reactant and product.
Okay.
Now, for SN1...
SN1 doesn't really have a hump.
It does, but...
Does it?
but it has a double hump.
What?
Yeah, because an intermediate is formed. So a transition state is something that does not exist by itself. Like this doesn't exist by itself. It's just a transition between the reactant and product. However, SN1, like, the leaving group leaves and it forms that carbocation intermediate.
The carbocation.
Yeah, which then could be attacked from either side. So that's why you have like the hump for the transition state, and then a little dip for the intermediate, and then another hump for the transition state, or for the different transition state, and then the product.
So you mean the two humps are because there's two possibilities of...
Oh, just because there's an intermediate that's formed?
Yeah, but the intermediate is going to be the carbocation, right?
Yeah.
And then the two transition states are what? The two possible... No, but there's no transition state.
Oh, there always is. I just didn't draw it here. But there's always a transition state. It's just something that doesn't exist by itself. Whereas an intermediate does.
But wouldn't a transition state be like something that's happening? Okay, I guess a transition state will be like the leaving group, like attached.
Yeah.
As
it would be like, I guess, like something taking the leaving group and the leaving group leaving. That would be like the transition state. Like in between these. And then
then there's another transition state in between 2 and 3.
Yeah.
Okay.
So these are just examples, but it's true for everything. Like so the hump is always a transition state, and it's always the highest energy part of a reaction, and since it's so high in energy, it cannot exist by itself. So this also is true for like like with enzymes, like we used to think of enzymes as just being like lock and key, right?
Right.
Like enzyme substrate. But what's the real like model?
It's
Like,
actually an enzyme substrate complex, right?
well, that's when they like, actually like come together.
So what do you mean? What's the real model?
All right, so this is, the lock and key, but the way it really works is induced fit.
Oh, yeah.
Yeah.
Sorry, don't think I'm stupid. I really know
Oh,
this.
no. Of course not. So it looks like, maybe something like this. And
Oh, I can see.
oh yeah. The other so like this could just fit into that. That's how we used to like kind of think of it, but it's more like like this, and then as they get closer, it would look more like the shapes will kind of change. So like here I drew it like kind of like that and like that, and then as they get closer, like there would be some type of like ionic interaction that'll change the conformation ever so slightly to make that fit like perfect.
Right.
And it's called induced because induced means that like something changes as it gets closer to something. Kind of like in chemistry you kind of have that, or like when you learn about like electrostatics and physics, like let's say we have something like some like neutral compound or neutral particle like this, right? And then let's say that we bring like some like very negative, like a little like like a glass rod or something that you like rub to make like it all negative, and we bring that close to this over here, and then it induces this dipole. Because as this gets close to that, it makes it so these plus charges move closer to that end because it's an induced, yeah.
But how is the induced fit model of the enzymes related? Were you going to tell me that it was related somehow to the transitional state?
Yes, because this here is basically a transition state because it doesn't exist in nature like this. Like it exists as this in nature and in this in nature, but as they combine to form that to actually once they actually combine, right? There's a transition state where their vicinity to one another induces a change in their conformation. So that's like a transition state right there.
Okay.
So like yeah, that's like a transition state, whereas this is just like whatever without a transition state. But there's always a transition state.
Cool.
Yep.
We forgot what we were talking about. I don't know what we were actually. Oh, yeah, about the difference between kinetic control and thermodynamic control. Okay, so I get it. Therefore, compound 2 will be more stable because we need to think of the formation of the larger liposome as a final product type of thing.
Yep.
But I'm sorry, but I still don't get what they mean by like compound 1 is under kinetic control.
Because it's just So okay, it can't be thermodynamic control because it's not changing the stability.
Mm-hmm.
Like here, maybe if I drew it like this. So like yeah, let's say that we just have like whatever, like a beaker or something, and we just threw all of this in there,
Mm-hmm.
and when we throw it in there, it's good. It's just gonna be like this, right? Like it'll just
Right.
it'll be like this is its final state because it doesn't mix, so it's just going to be fast. Whereas for compound two, if you threw, this into like a beaker, right? It'll be this initially, but over time it will turn into that.
Mm-hmm.
So this takes time to make the most stable product, and this doesn't change its stability, so it's just fast. So, so like kinetic control deals with speed, and
Mm-hmm.
thermodynamic control deals with um, stability.
Okay.
Yeah.
So we cannot assume that these small ones were formed already, pretty much.
Uh, wait. What's that?
The small liposomes instead of the big one. So like uh yeah, if we threw like compound one in a beaker, then it's gonna form the different sizes, right?
So
It's
they
gonna be
already
fast.
started. So see where it says mixed liposomes of different sizes.
Mm-hmm.
So that's what that is. They throw that into the beaker. So these are different sizes.
Okay.
Yeah. So like
All right.
see how like this is a size, this is a size, this is a size, this is a size, right?
Mm-hmm.
So they mix this in with that and that and that, and they didn't see any change. They were stable to mixing, and that wording is what threw me off because thermodynamic control means more stable,
Right.
but it
And
just
also
is.
because you assume that if they don't
Mhm.
change, it's because they're stable. But
Yeah, so they don't change because they are stable on their own. However, compound 2 formed new lysosomes that are even more stable than if they were alone.
okay.
Yeah.
Cool.
Mm-hmm.
Diameter, deep versus solution, volume. It is like a math. Let's see.
Oh, you're on the next one? Okay, let's see.
Yeah.
Diameter D versus elution volume for liposomes. Diameter, volume. Okay, so that's elution volume, not necessarily the volume of the liposome itself. So we can just look at, the different things on the chart on Figure One. Not the chart. I meant Figure One.
Mm-hmm.
So, it seems okay. So it seems like it says that. Oh wait. Okay, so they're saying that what concentration of lipid is necessary to prepare liposomes with a diameter of 250 nanometers. So, oh, interesting. Okay, so
Yeah, so it's not so let me see if I understood the question. It says we would have to look at the figure that is giving on the actual question to determine the volume, the elution volume for that particular diameter, right? But we don't have it there. We have 200, 150, 150
Yeah. So we're gonna have to make, do some
estimation.
inductive reasoning. So,
Mm-hmm.
okay, what we see here is, so at like, okay, so that's 15. So like, in between 10 and 15 is the point 0.2 concentration. So
Wait, I'm not looking at what you're pointing out. Okay, in between 10 and 15. Okay.
yeah, is the point 0.2 concentration.
Mm-hmm.
So that would be correspond to, between 10 and 15. So something like like something like here, right, in between this and this.
Okay.
So it's not going to be point 0.2, because point 0.2 is like, the elution volume of point 0.2 is between 10 and 15, right?
Hold on, give me 1 second.
Mm-hmm.
Elution volume. One is why do they do that? They're
What?
giving everything in nanometers instead of not nanometers. Yeah, nanometers instead of what is it that they're giving? They're changing the units for
Oh, yeah,
millimolars to
yeah,
no,
but
wait, I'm
it doesn't
confused.
yeah, it doesn't necessarily matter because we don't have to do any math. We just have to look at what the graph corresponds to, right? So like for instance, at concentration point 0.2, right? Like you see where my cursor is?
Mm-hmm. So wait, give me 1 second. We
Mm-hmm.
can already get rid of 10.20. We can already get rid of A. We can already get rid of B and C. It's D.
Yeah.
Oh, sorry, I didn't look at the
Oh,
I
no, no,
didn't look
no.
at the correct answer. I swear.
Yeah.
Okay, because what I was trying to do is like, okay, if the elution volume for a diameter of 200
Mm-hmm.
was 10 milliliters,
Yeah.
then it needs to be more than 10.
Mm-hmm.
It needs to be more than that concentration for 200 since it's 250.
Yeah. So I would kind of like look at it like this, like diameter and elution volume are inversely proportional, because as
Okay,
diameter
sure.
decreases, elution volume increases, right?
Mm-hmm.
And so, that's also reflected here, but with concentration.
Right.
So, okay, what I would write here is,
And you wrote it down at some point. You said that that concentration was inversely proportional to elution volume.
yeah, right here.
Oh, there you go.
And
Mm-hmm.
then I would write what they're showing us in this problem. So, um, I would also write like diameter is inversely proportional to elution volume. So they're asking for a diameter of 250, which is greater than, which is higher than the amount that they have, right? And since that's inversely proportional to elution volume, right? Um,
Mm-hmm.
so and so is the concentration. So it should be a concentration that's greater than the highest concentration we have, because yeah, this thing is like between 10 and 15, and between 10 and 15 is between a diameter of 200 and 150. And since they want 250, it would have to be a volume less than 10. So, and a concentration greater than 0.2. But yeah, I think you understand it, right?
Mm-hmm.
Okay,
Yeah, but the way you put it. Okay, yeah. No, but I get it.
good.
Mm,
The next one
okay.
is just like a math one, I suppose.
What mass of compound 1 is contained in the solution used to prepare liposomes that elute 20 mLs. Okay. Sorry, you probably already answered that question.
Mm-hmm.
It takes me a while to process what they're asking me. So so at 20 mLs, you're gonna have a concentration of 0.10 millimolars, and then you know that the grams per mole is 800. So you just have to divide that per mole. I guess I know it's simple, but then when I see units that I have to change, it's freaking annoying, and then I probably get it wrong.
All right. So
I just have to divide the molar mass by the number of moles, and that's it.
But the thing is, we have to find the mass, right? So we have concentration, we have volume, right? Right.
So if we have 0.10 millimoles and each mole is 800 grams, and
but we don't know the number of moles though. So here, I'll write down what we know. So we know the molarity is 0.1 E negative 3 molar. We know the volume
that's true.
is 20 E negative 3 liters. So how do we get moles?
We just divide by the... So
what's a molar?
This molarity is 0.1 moles per 1 liter. So if we have 0.1 in 20 times 10 to negative 3, we just have to divide it.
Well, okay. So think about it like this. So 1 molar, what is that unit like equal to?
The amount of moles of a certain solute in a liter of solution, right?
Moles over what?
Per liter.
Per liter. So a liter, right? So basically volume, right? So if you multiply molarity by volume, you should get moles, right?
Right.
So if we multiply these guys, we would get moles, right?
Yes.
Okay, and then we can use that to figure out the mass. All right. So okay, like mv is equal to the number of moles. So I'm going to do it like this. I
don't think you're writing on the... I think it froze.
Oh,
I don't know.
One of our services is down. What the hell? Experiencing a temporary outage. We'll try again in a few seconds. That's nonsense. Okay, this is kind of going a little faster now. Okay. So I'm going to multiply these. And I'm going to do it like this. 0.1 is 1 over 10. E negative 3 times 20.
Oh, no, it's not loading. Shit.
20.
It's fine. I'll just do it here.
Okay. Times 20 E negative 3. Oh, all right, whiteboard's back. So this is how I would do it. 1 over 10 E negative 3 times 20 E negative 3. 10 goes into 20 twice, so I get 2 E negative 6.
Negative 6, okay.
So you see how instead of writing 0.1, I did 1 over 10? and then 10 goes into 20.
Mm-hmm.
So, like, I didn't have to turn this into 1 times 10 to the negative 4. I didn't have to turn this into 2 times 10 to the negative 4, I guess.
Whatever it is.
Yeah. so okay, I get this
wow.
as the number of moles.
Mm-hmm.
And then they give us, grams per mole, so I multiply it by that, right, to get the number of grams. So I'll just do 8E2 grams per mole. And then I get 16 E -4 grams. Oh wait, no, I did something wrong.
No. 16, 2 times 8, 16, and then you're multiplying, so it's -4. Oh, wait. Oh, no, never mind.
Yeah, because all the answers are in.
Is it?
What mass of this is contained? Oh, I see. I see what I did. Liposomes were synthesized from 1 ml of compound 1. So this over here, 1 ml of that is compound 1. So we're not using the 20 ml. Yeah, 1 ml is what we use. So my
1
bad.
ml at different concentrations.
What's that? So the 20 ml thing is just to tell us the concentration, but
it's
not
just
the volume.
What concentrations are?
So the 20 ml elution is just there to tell us what concentration we're going to use. But since we're trying to find the mass of compound 1 and 1 ml of compound 1 is added, that is what we use for volume, not the elution volume. So
hold on, give me 1 second. Let me process that.
Mm-hmm.
What mass of compound 1 is contained in the solution used to prepare liposomes that elute at 20? What does it mean that they elute at 20 mLs? So you're using 1 ml for all of them, right? And then so there's 1 ml of at a concentration of 0.2
let's
moles
say this is the size exclusion chromatography thing, and this is the amount that is eluted, 20 ml. So that's like after you do the size exclusion chromatography, you end up with 20 ml of the 0.1 millimolar solution. However, that's just how much is eluted. That's not how much compound 1 there is. There's only 1 milliliter of compound 1.
So how are you getting 20 mLs eluted?
Oh, that's like they give you, so the elution volume is just this thing over here. So for the purposes of this question, elute at 20 ml is just to show us what concentration to use. And since they're asking about compound 1, and we know that compound 1 ml was used at various concentrations, so all of these have 1 ml of compound 1.
Mm-hmm.
But this is the elution volume. It's not the volume of like the aliquot. So you know what? Here, let me talk about aliquot then.
Yeah, so what I'm confused is like, what is the elution volume?
So So an aliquot is basically the sample that they use. So like 1 ml of compound 1 in an aliquot, and then they throw that into this, size, exclusion, like chromatography thing, and then, elution is just how much of the overall thing is coming out.
But like, how can you get 20 mLs if you just threw in 1?
Because it's 1 ml of compound 1.
But it's 20 mLs of that solution.
That's eluted, yeah. Since it's 1 ml of compound 1, they mix that into the solution, and you get, because in here there's also liposomes, right? Probably solvent, right? And they throw that into here, and also dye, right? So that's an aliquot.
Okay.
Here. Aliquot, a portion of a larger whole, especially a sample taken for chemical analysis or other treatment. So, yeah, this is what I was trying to draw right here. They're in these small, kind of things. I don't know if you've ever worked with them.
Oh, yeah.
Yeah. So that's what an aliquot is. So
okay, so how come so when you say 20 mLs were eluted, it's 20 mLs of that particular solution that has a concentration of 0.1 millimoles? Okay.
Yeah, and they helped us out by making all the answers have an 8 in it, because I'm sure a lot of people, including myself, would have put down, if the choice was 16 or something that I got, would have put that down. But yeah, the main difference here is just between elution volume and volume of compound 1.
Okay.
That's the main difference that you have to know here.
So then what we would have to do is it's only 1 ml.
Yeah. So we're going to do the same thing, just with a different value for volume.
Yeah, so instead of 20, it was going to be only 1.
Yeah.
So it's basically it's just 0.1 or 1 over 10 times 8E2 for 1 mole. Oh, okay, got it. So it's wait, give me one. So I get 0.8 E2.
0.8 E2.
Because it's sure 1 over 10 times 82 grams over 1 mole, right?
82 grams per 1 mole, but your moles should be 0.1 E neg 6.
Oh, that's E negative 6. Yeah. Okay, so that's E negative 4. So it's 0.8 E negative 4, 8 E negative 5, 8.
Oh. Yeah, and then after that, we just have to look at what it turns into in the choices. So 80 E neg 6 is 80 micrograms.
Micrograms?
Yeah.
Okay.
So your answer is A.
Got it.
Okay.
I have a question. I have a couple of questions that I wanted to. Well, I was doing some psych questions earlier today, so I wrote down the question that I had that I wanted to show you. I want to share my screen, and then on a couple ones that I did on bio. like 2 days ago.
Okay. I don't remember much about psych, but I'll try.
It's only one.
Okay.
Can I? Oh, got it.
Yep.
So this was basically, I was gonna send you an email with it, so that's why I wrote down my rationale for it. But basically, this is just a question, and it was a discrete question, so it was not based on a passage.
Okay, so operant extinction is when you treat the thing that you uh, teach uh, leaves, like it's no longer there. Instinctual drift, I think that's when they revert to their instincts. Maybe stimulus generalization is when like a particular stimulus that causes like a response is wider. So a lot of things that are like that stimulus have that same effect. Partial reinforcement, I don't think that's a thing. Or
It's
if it
just
is
a
a
different
thing,
reinforcement schedule. So
oh yeah, I remember hating hating the reinforcement schedule stuff. So okay, avoid when training a rabbit for television commercial. Um, geez, I don't even know. I mean, uh, I guess it won't be partial reinforcement. What is he trying to avoid? Stimulus generalization would be good, I guess. Um, Operant extinction and instinctual drift both involve things that are taught not no longer being there. Maybe? Okay, let's see. You said you chose C, right answer is B.
yeah, so basically the right answer was instinctual drift, but
Mm-hmm.
so then when I went to look it up on the internet, it basically gave me a bunch of like examples that they've done before with other animals for like TV commercials. Like for example,
Mm-hmm.
there was one with a raccoon that they were trying to train them into like put coins into an ATM or something like that, and there was one with pigs trying to get them to put coins in a piggy bank. And then they were saying that all they're doing is avoiding instinctual drift because
Okay.
eventually this is going to lead to, they're not going to be trained well. So, for example, what they did is that for the raccoons, because they have this instinct of like grabbing something and just like moving it around in their hands,
Yeah.
what they did to avoid this instinctual drift was to actually train them with bigger objects so that they wouldn't grab them again and put them around in their hands. And so I was like, that's like to me it didn't make any sense. And the reason why I picked option C was just because of the TV commercial part, because I assume it was like, okay, you're gonna be like training the animal under a lot of like stimuli. So you
Yeah.
don't want the animal to react similarly to something that you might be using as your actual neutral stimulus. So for example, if you're using food and then you're not avoiding stimulus generalization and there's someone else with a thing of food next to the
Uh
animal, so the animal is going to respond in the same way.
huh. So I mean, I was looking at A or B because those things both involve things that you teach no longer being there. But maybe, I mean, at least that's what I know about extinction. Maybe the operant part I was wrong on. He said operant extinction will make the neutral stimulus ineffective. Okay, I guess
Mm-hmm.
that's for neutral. So if it's neutral, it's not something that you teach. Like, um, yeah, an instinctual drift. Here, let me see. Operant extinction. Gradual decrease in the response rate of a behavior learned via reinforcement. Okay, that's what I was thinking. And yeah, okay, so what's the difference between that and instinctual drift? Let's see. I see literally that question when I look it up. Instinctual drift, established habits learned using operant techniques are replaced by innate food-related behaviors. That doesn't. Oh, I see the piggy bank thing that you're talking about.
Yeah, I mean, like, I still don't know why it's instinctual drift, but I guess, like, to
I know
me,
why it's
and
that.
I
I just
even
don't know
wrote,
why.
like,
Yeah.
all of these answer choices seem to be like things that the trainer will want to avoid when training an animal, just because they're like bad things, even partial reinforcement, because I remember reading somewhere that
Oh, I
whenever
see. I
you're like,
see.
what's that?
I see. So, I mean, I knew that it was going to be either A or B because both involve things that you have taught the rabbit no longer, like, the rabbit basically forgetting it, right? So, I looked into Operant Extinction, and that actually is stopping to reinforce behavior that has previously been reinforced. So they have the same result, but operant extinction is what you do for that same result, if that makes sense. Like, so what I see when I look it up is removing reinforcement from a previously reinforced behavior in order to eliminate that behavior, no longer reinforcing something that was once reinforced. Thin the reinforcement ratio, you will get an extinction burst. So, will an animal trainer most likely try to avoid when training a rabbit for a television commercial? Maybe it has to do with the word phenomenon. Because operant extinction is a method.
I thought operant extinction happened whenever the neutral stimulus was no longer eliciting like a conditioned response.
Yeah, so
like, let's say when you stop like pairing the neutral with the unconditioned one.
Yeah, there's a difference though okay, so let's see. So in between the two, right? So let's see. Operant extinction.
I'm gonna stop sharing.
Versus what was that? It was like evolution or something.
What? Instinctual drift?
Oh yeah. Operant extinction versus. Oh yeah. I'll share my.
Oh, sorry, I stopped sharing. I thought that you were gonna show me the whiteboard, so
Yep.
I was like, oh, okay.
So operant extinction versus instinctual drift. So okay. So okay, this is like a method of reaching that.
Right, so instinctual drift happens due to operant extinction, or it can lead to operant extinction can lead to instinctual drift.
Yeah.
But
so
operant extinction is not something that you purposely do. It's something that happens whenever you stop pairing the conditioned stimulus with the unconditioned.
So that is something you do, right?
True.
Whereas instinctual drift is so like one is a method and the other is the phenomenon. So operant extinction is something you can do by stopping or lowering the amount of reinforcement you do to like an animal or something, which results in the phenomena of instinctual drift. That animal will go back to instincts.
Right.
So
So you
that.
would say that
Mhm.
what was the other one? Stimulus generalization is not a phenomenon?
Uh, mm, I mean, it might be, but I just knew right away that it would be one of these two
Mm-hmm.
because these two are the opposite of like training or teaching because they both revert back to like it go like the thing that's learned is gone.
Right.
Stimulus generalization, like you know, like I think that it would be more um, something that you would want because you want the rabbit to be able to have multiple stimuli coming in and generalize them and still be able to do the task that you teach the rabbit. Um,
Mm-hmm.
I said task that you teach the rabbit, and there's a company called TaskRabbit. But so yeah, so it wouldn't be that, and then I forgot what the other choice was, but I knew it wouldn't be that
Oh,
either.
partial reinforcement, but I
Yeah,
didn't
so
really
that's
think of that one.
yeah. So yeah, that's really tricky question, and the only way that I can see that that it's not operant extinction is just because they said phenomena.
Okay.
That's yeah, but
Right, and
yeah,
partial reinforcement is not a phenomenon either, so
yeah.
it's
I
actually a
think
method.
yeah, maybe like stimulus generalization is a phenomena, and the method that you use. I don't want to use method to define method, but like what you use to achieve a phenomena is the
Mm-hmm.
method, I suppose.
Got it. I think that was the only one I had. Um, Let me find the one that I told you for.
Oh yeah, and then here's stimulus. Oh, never mind. Okay, what was the other one?
I know that was the only one for psych. I'm looking the one for bio.
Mm-hmm. Oh wait. What are you looking at?
The ones that I had questions for, like that I went over, like I saw and I was gonna
Mm-hmm.
ask you about them.
Okay.
Just give me 1 second. There was something on metabolism, but now I can't find it. Okay, so it's question. Oh, but it's still so passage 11,
You
question
want to share your
one.
screen?
What's that?
You want to share your screen?
It's oh, okay, sure. Give me 1 second. Where do I have Zoom? Okay.
Okay. So, oh yeah, and we could go over this section bank too if you want. Um. Oh yeah, this. So like this is like the things
Not fun.
in metabolism that you have to know, I suppose. Let's see if I can do it without knowing it. After depletion of hepatic glycogen, what can be used as precursors? So okay, glycogen is maybe gluconeogenesis. So we're gonna have I know it'll be, well, okay, gluconeogenesis, making of glucose from some precursors. I think there are like 3 precursors.
Mm-hmm.
Um, all right. Hepatic glycogen stores are soon exhausted, and the glucose pool must be replenished from non-carbohydrate sources, including fatty acid and glucogenic amino acids.
Where
So
are you reading that?
at the end of paragraph 2.
Oh, okay.
So we're looking for non-carbohydrate. So we're looking for glucogenic amino acids, which aren't there. So okay, non-carbohydrate sources. Wait. Okay. Hold on. Um. Okay. I just have to remember what is used in gluconeogenesis. Maybe uh, alpha ketoglutarate, oxaloacetate. I'm pretty sure oxaloacetate is used. Maybe acetyl
But that's
CoA.
already like part of the Krebs cycle, so like it wouldn't help to sustain blood glucose levels. Oh wait, but it's gluconeogenesis. So you're actually depletion of hepatic glycogen in newborns can be used as precursors to make glucose.
Mm-hmm. Okay, let's see. Okay.
I guess I didn't. I was thinking more of like reversing glucose, like reversing glycolysis type of thing. But basically, it's asking like which of these compounds can be used to just start gluconeogenesis.
Um, Precursors to sustain the blood glucose level. I was gonna say lactate is not something, but it is because Roman numeral 2 is in every choice. So lactate must be something that is used. Okay. Okay, that kind of makes sense. All right. Let's see what else then. Salicylacetate, alpha ketoglutarate, acetyl CoA, 1, 1, 3, 3, 4, 4. Yeah, this is something where knowing, I suppose, parts of metabolism definitely helps. I'm trying to see if I can figure it out without it, though. But I'm trying to place in my head where alpha ketoglutarate is. I guess it's like in the Krebs cycle. Or is it in glycolysis? Alpha ketoglutarate.
It's in the Krebs cycle.
Krebs cycle. Alpha
Yeah.
ketoglutarate. So acetyl CoA is what goes into the Krebs cycle, mixes with oxaloacetate to produce citrate, then isocitrate, then maybe alpha ketoglutarate.
See, that's the thing. Like all of them are part of the Krebs cycle.
Yeah. But I know that oxaloacetate can like come out of the Krebs cycle and I think goes into the gluconeogenesis. So 3 I am leaning on. So the ones that have 3 have So it's a matter of 4 alpha ketoglutarate. I mean, so okay, for the test, know those things.
Okay.
But as for like so okay, I'm pretty sure about the oxaloacetate. So that leaves me with either choice B or choice D, and that means that I have to see what happens with alpha ketoglutarate.
Mm-hmm.
So alpha ketoglutarate, does that do anything? I know it's there, so I'm guessing it's after isocitrate, alpha ketoglutarate, and then I think it's like succinyl CoA and then succinate, and then I think fumarate and malate and oxaloacetate. Alpha ketoglutarate. That. I'm gonna go with no.
Would be.
B, lactate and oxaloacetate. Yeah. Let's go for it.
Do you want me to click it or like?
Yeah.
Oh, I was like, I don't know if he's doing it in his.
Damn it.
Yeah.
Okay. So yeah, I was between the two, and I just was like, I didn't know what alpha ketoglutarate did. Let's see. Lactate, oxaloacetate, and alpha ketoglutarate, gluconeogenesis. Okay. So, I mean, yes, for the test, know those things. I just didn't have them memorized, but I did know that it had to be gluconeogenesis, and knew that oxaloacetate is something that can go into gluconeogenesis. Lactate, I initially was like maybe not, but it is in all the choices, so it must be. So that's probably a non-carbohydrate source of something. But alpha ketoglutarate, I just I guess I didn't remember. Let me look at my metabolism thing. Gluconeogenesis, 3 carbon precursors like lactate, alanine, glycerol, okay? Turn to pyruvate in the mitochondrial matrix of liver cells or to the cortex of the kidney, where pyruvate carboxylase turns it into oxaloacetate, which is then blah, blah, blah. Okay. Oh, metabolism brain dump. It should be here. I still don't see anything about alpha ketoglutarate. That's pretty weird. Let me see. Gluconeogenesis. Alright. Wait. Okay. Alright, I guess, yeah, that's one of those things you gotta know.
Have to know.
Yeah. Yeah. So Anki can help you out there.
Okay.
because I definitely have like cards about like the metabolism stuff. But yeah. Um, so yeah.
Okay, so I thought that there was like maybe another because I was like I was
Does it make sense
also
that it's gluconeogenesis though?
yeah, but I was thinking more as like reverse, like the reason why I discarded oxaloacetate and alpha ketoglutarate and all of that, I was like, that's way past glycolysis, like that's already where glucose is it's broken down. So there's like I can't really sustain blood glucose levels. Now if they were talking about like respiration, like cellular respiration, I would be like, okay, yeah, those are part of the Krebs cycle. But I guess when I read with you after the depletion of hepatic glycogen,
Oh, I see the alpha
then which
ketoglutarate thing.
compounds can be used?
Here, let me share my screen for a sec.
Let me stop sharing mine.
Okay, so wait. So this is like I kind of showed you this, right? You know what? I'll copy it to your notebook, but I kind of did this giant thing. You see it, right?
Whoa,
Yeah, so I did this giant thing for
that is really cool.
Mhm. Yeah. So basically like
Oh my
here.
God, you did that or one of your students did that?
No, I did that.
Oh.
Uh-huh. So so okay. Um Krebs cycle whatever. Then here is where gluconeogenesis happens, making glucose over here.
Mm-hmm.
So oxaloacetate. So like okay, in the mitochondrial matrix, pyruvate can turn into oxaloacetate, which can't leave the cell, can't leave the mitochondria because it has to go through either a malate or aspartate shuttle. So it goes through that to enter the cytoplasm, and it turns into the aspartate through the addition of alpha ketoglutarate turns into oxaloacetate, which goes through kind of like the reverse of glycolysis, but not exactly the reverse of glycolysis to make glucose. So that's alpha ketoglutarate right there. Um, yeah, and then I have like a brain dump here where I try to make these things like smaller, or like simpler, but
Mm-hmm.
not simple enough to include alpha ketoglutarate. But yeah, it's what
Okay.
turns aspartate into oxaloacetate. So that's why it's needed.
Okay.
As for lactate, okay, yeah, lactate is. I was only thinking of this, so I wasn't thinking that would play a role. But lactate is, um, like a 3-carbon precursor because it basically looks exactly like pyruvate.
Wait, but you have lactate there.
Yeah, here.
So why you were not sorry.
Bless you.
Why you were not thinking
Oh yeah,
about
you know,
lactate?
I even made a Anki card about this. Um, like essentially how like aspartic acid turns into asparaginine, right? By
Mm-hmm.
turning like the carboxylic acid into an amide. So I
Okay.
did this just to talk about the amino acid change, but I just realized that this is exactly what is relevant to that previous question because we have oxaloacetate and it turns into aspartate through the use of glutamate, which turns into alpha ketoglutarate. And once it's aspartate, it can leave through the aspartate shuttle out into the cytochondria. Whoa. Out of the
Mitochondria.
mitochondria and into the cytoplasm. And then it would go go from aspartate into oxaloacetate, like reverse, through the addition of alpha ketoglutarate, which would put an arrow in that opposite direction. Yeah. So
Okay.
yeah, I'll send you like this deck, but yeah, those are.
I think I had. Was that like the question? Well, you sent me 2 decks already, but that's fine. You can send it again.
Yeah, this is like the one that I made with new things, and I combined the 2 previous decks into this.
Mm-hmm.
Yeah. So those are the things to know that you do have to know, unfortunately.
Okay, no, it's fine.
Yeah. Okay. What's next?
Let me check the time. Oh, okay. Oh, it's actually here in the. So question 12. Do you want me to share my screen again?
Is this the BB section bank?
Yeah.
Okay, I can go to that.
Before you go to 12, if you don't mind going to 10, since they're both based on the same passage.
Okay. Okay, 12 antibiotic treatment. Alright, yeah, BB sections are the worst. I mean, passages are the worst because the charts and stuff are really hard to interpret.
Okay.
I
mean, I can tell you how, because I picked C and the right answer was A. And wait, the only reason why 12? I picked C was because I even looked at the graph and everything, and I understood it. It took me a while. This passage was hard. I mean, it was a little bit confusing.
What does the question start with? Because my 12 is like compared to.
Oh no.
Yeah.
It's so it's first is 10 and then 12.
Okay. 10. All right. Let's see. What conclusion about glucose uptake is best supported by the data in Figure 2? Figure 2. We basically. So I'm going to read a little bit above. Relationship between GPCR43 function and insulin sensitivity. Adipocytes from wild type and the mutants that don't have GPCR43. WAT. Is that white adipose tissue or something? Oh, yeah, white adipose tissue. Okay. We're incubated in the presence and absence of both insulin and acetate, and the reuptake of glucose was measured. Okay. So first of all, I'm only going to look at the one with the asterisk in Figure 2.
Okay.
Do you know why?
Because those are significantly.
Statistically significant.
Statistically significant.
Mm-hmm. So that's all I'm going to look at, and it seems like they're giving the wild type mice insulin in both cases, but acetate, when it's not given, there's a lot more glucose uptake compared to when acetate is given, there's less glucose uptake. So it seems like acetate works to suppress glucose uptake in wild type adipocytes. And then, but not GPCR, whatever the mutant ones.
I know that for this question, and that was kind of stupid, I know the role of insulin, and I know it works in glucose uptake.
I mean,
but
you don't even
for
have to
whatever
know that.
Reason,
if you just look at
you can
like
if you didn't know about insulin, you could also deduct that because in WT, like the last WT and the last GPCR43, like those two groups, because it decreases the glucose uptake whenever there's also insulin present. Because acetate is present on the first WT and the first GPCR43. And yet the glucose uptake doesn't change. So what I assumed was that insulin was actually suppressing glucose uptake in the presence of acetate, because when insulin was not present, the glucose uptake was not changing.
So all you need to look at is just like, okay, so here, insulin, no acetate, glucose uptake high. Here, insulin, acetate, glucose uptake not high. So acetate works to reduce glucose uptake, right?
Mm-hmm.
And you don't have to know what insulin does or what acetate does. It's just right from here, and this is glucose uptake, right? And then compared to everything else, right? Acetate, insulin, doesn't matter. It doesn't matter if there's insulin, doesn't matter if there's acetate, doesn't matter if there's acetate but no insulin, doesn't matter if there's...
Got it. I know what you're saying. You just tell me to focus on that WT, like that difference, saying what is present, what is not. Insulin is present in both, acetate is not. So acetate is the one that's suppressing. Simple as that. That was stupid. I don't know why I picked insulin.
Well, I mean, oh, okay. You said insulin suppresses glucose uptake in the presence of acetate, but not GPC. Okay, all right. So the difference between A and C is which is the one that suppresses.
It's suppressing.
So, like, I guess, like, because C is saying when acetate comes into the picture, insulin is like, all right, I'm going to start being bad or something.
Mm-hmm.
But that's kind of like a stretch. It's easier to just see that acetate is the one that's bad.
Yeah, if you only, yeah, it's true. It's absolutely true what you're saying. I just started comparing across the whole thing. Mm-hmm. And I saw that acetate was present on the first two groups, but insulin was not. So,
but that didn't change anything, right? Because these are pretty much equal.
Yeah, I don't know why I thought. Oh, okay. No. I actually know why. So, for the GPCR43.
What, the mutant?
Insulin suppresses. Yeah. No, the second group of GPCR43.
Okay.
Okay. So their insulin is present, right? In both of them.
Mm-hmm.
But then if you compare that to the second WT group, you're going to see that glucose uptake is decreased when acetate is present. But okay, no, I understand. You're absolutely right. I don't know what happened. I was just, I guess it was like 12:30 a.m. in the morning, and I was like going through these questions, and
I think the asterisk part maybe you overlooked. So you were looking at all of it. Mm-hmm. And so if you looked at this, you see that like there's a tiny increase from left to right.
Yeah.
But the entire point
right
of
to left.
There's a tiny increase there, but the entire point of the asterisk means that there's essentially no difference between the two. So even though it's like a tiny increase, it's really the same. So like this bar and this bar are equal. These two bars are equal. These two bars are equal. And that's because of like, the error bars. They overlap. Because, what I mean by error bar? Because this can be
so if there is any overlapping
there,
of
right?
of the error bars, then there's no significant difference.
Correct, yeah. So for this question, I would go right to this and then see what's different from here and here. No acetate and acetate. So acetate must work to block the reuptake.
Okay.
Mm-hmm.
And then question 12, it's also related to that passage.
Okay.
So I picked or just read it.
Oh, you said 12?
Yeah.
Compared to untreated wild-type mice, antibiotic treatment of wild-type mice is likely to result in... All right, let's see. So we have... Okay. Oh, okay. So, the catabolism of dietary fiber by gut biota, or whatever, results in the production of short chain fatty acids such as butyrate and acetate, which are important energy sources for the host. Okay? So, if you give antibiotics, energy sources, okay, then let's see. GPC, okay, so energy source in the form of SCFAs, which act as signaling molecules that bind to GPCRs. So there's a particular GPCR 43, and that's in white adipose tissue, but not in the muscle or liver. Okay. So, alright, so if they gave antibiotics to wild-type mice, it would stop the catabolism of fiber, so it won't make those SCFAs, which means that it won't bind to or activate GPCRs. And okay. So if they don't bind to, if there's nothing to bind to GPCRs, I mean, okay, so if you give them antibiotics, the microbiota is going to die. The fiber isn't going to be catabolized. Short chain fatty acids won't be made, it seems. So nothing will bind to the GPCRs. So okay. So butyrate levels will decrease, not increase, right?
Exactly.
Okay.
Well, that's true because then they would not be. No, they would actually. They will decrease because there's no gut microbiota to process those fatty acids.
Yeah. Here, I'll do like the thing that I do with like passages. So basically, let's see. Fiber through like microbiota turns into SCFAs, like whatever, butyrate, acetate, and these work to, or rather they bind, to GPCRs, right? So if we had an antibiotic, it would destroy the microbiota. So you're not going to have these guys made. So butyrate levels should decrease. So A is gone. Right. Now let's look at, body mass, insulin sensitivity, increased volume of adipocytes. So it seems like, let's look at figure 1. So it seems like if we compare, let's see. If I compare wild type standard diet to wild type high fat diet, the high fat diet ones have greater body mass?
Yeah, so whenever there's a GPCR, so the ones that don't have the GPCR receptor, they actually have
Oh,
higher.
okay. Um, okay, all right. So I'm gonna.
So I wrote here like absence of GPCR equals weight gain or
So all right, if we compare, so okay, wild type, standard diet, um, versus wild type high fat diet. Um, so okay, standard diet and high fat diet. Okay, so like high, you know, body weight. And then now if I oh, wait. All right. We can draw this. I'll do this better. So okay. Wild type standard diet body weight is less than wild type high fat diet body weight. And then I'm going to compare the GPCR mutants and pretty much the same thing. So GPCR mutant, standard diet. Okay, I can do this even better. Just from lowest to highest. So wild type, standard diet, GPCR mutant standard diet, then wild type high fat diet, and then greatest increase in body weight is GPCR mutant high fat diet. So you see what I did there?
yeah.
Okay, so that's just me making sense of the graph.
Mm-hmm.
So it's okay. So now, all right, antibiotics would destroy the fiber. I mean, sorry. Right, production of short chain fatty acids. Examine the relationship between GPCR function and insulin sensitivity. Okay, and then let's see. So A is out, decreased body mass. Oh wait. Oh, okay, wait. GPCR 43 is not in the muscle or liver. Analyze contribution to energy regulation. Okay, so to explain these, so it seems like oh wait, I forgot the R there. So it seems like so if when they're fed the same diet, the absence of GPCR results in greater like body weight. So that basically tells us that GPCRs function to reduce body weight.
So whenever there's no GPCR, so the mutant ones, the GPCR 43 negative, are the ones that don't have the GPCR.
Yeah.
And they both had higher body weight compared to the wild type, which had the GPCR.
Yeah. So
GPCR will lead to increased body weight.
Well, GPCR, the ones who don't have it have higher body weight, right?
Right.
So GPCRs would reduce body weight, right?
would increase body weight.
That's if they don't have it, though.
Oh, wait.
Mm-hmm.
Would increase body weight.
Yeah.
Would reduce body weight because
Mm-hmm.
the ones that are wild type actually have less. Okay.
No, the ones that are wild type have GPCRs.
But
And
weight less.
yeah, when the diet is the same.
Okay.
So we know that it's not due to diet.
Okay.
So GPCRs work to reduce body weight, right?
Mm-hmm.
So if we had antibiotic treatment, right? Microbiota's gone. So that means these aren't made and these don't bind to the GPCRs, which work to reduce body weight. So it should work to increase body weight mass, right? So B is not going to be the answer.
Yes.
Okay, so B is out. And then insulin sensitivity is the last one. And increased volume of adipocytes. So I guess they did the testing of insulin sensitivity in figure 2.
Right. Well, pretty much. So that's why I honestly went by D because I was like, okay, if acetate suppresses glucose uptake, it's going to increase insulin sensitivity. Because acetate is one of the short chain fatty acids.
So acetate works to decrease
To decrease
glucose uptake, right?
which increases
Like gluconeogenesis
or decreases insulin sensitivity. So if acetate is suppressing glucose uptake, so you will need more insulin to uptake the same amount of glucose, so the sensitivity will be decreased.
Yeah. Mm-hmm. Yeah, like from the last question or whatever, the acetate presence makes the reuptake of glucose or uptake of glucose lower, and insulin, works to uptake or to, take insulin from our blood and uptake it. So, so if we block the making of acetate, there should be more uptake, right? And therefore increased insulin sensitivity, right?
Oh yeah, that's true.
So, and C is the only one that says you're getting fatter. So it should be C.
I don't know why. Yeah, I wrote, so the reason why I said that, or like I walked myself through the right answer was because, so I said antibiotic treatment equals no gut microbiota, which equals no production of short chain fatty acids, which equals to no GPCR activation, because it says on the passage that they bind to GPCR to activate it.
Yep.
So then if I actually go to the figure 1 and see that the ones that don't have GPCR are the ones that have higher weight, I just assume that no GPCR activation is the same as not having a GPCR, so that's why it leads to higher volume of fat cells. But I guess I got confused with,
I mean, that's right.
the fact that that acetate was one of the short fatty acid chains, and it was suppressing insulin. Yeah, I guess I got confused with that.
Yeah. So I wrote like acetate inversely proportional to glucose uptake, and since glucose uptake is done by insulin, it'll also be inversely proportional with insulin sensitivity.
Okay.
Make sense?
Yes.
Okay.
All right.
What's next?
I think we're done with the time since it's like 4:30, almost 4:30.
I could do like another like 3 minutes.
Okay. So let's see, we did that one, 12. That one was the one that we just did. We can do another one for physics because I didn't really have any other question on the bio.
All right, which one?
So let me see which one was next. Oh, why? I'm gonna share my screen.
Okay.
Doesn't give me the.
Okay, let's see. Oh, we did this, remember?
Did we?
Mm-hmm. Yeah, it's in
I
your
don't-
notebook. And I think you got it right also. But anyway, we would just do, the delta G is equal to negative RT, uh, natural log of, I think like ADP to ATP.
Mm-hmm.
And then, ADP times here. I'll ADP concentration times AP concentration. Here, I'll go to.
Oh, but if it's in the notebook, don't worry. Maybe I didn't see it.
Yeah.
And that's weird because I would have answered it and I didn't answer it. I guess I forgot to answer it.
Yeah. Here. It's over here. You see it?
Oh, I can't. You want me to stop sharing?
Okay. I made it so both of us can share, but yeah, here.
Oh, okay, got it. That's weird that we didn't do it before. Yeah, now I remember it was probably through the end of the session, and that was probably why.
Mm-hmm.
Okay.
Yeah. Show me like another one, and then we can do that.
This is discrete. I'm surprised like we haven't seen like most of the questions that we have done are like chemistry based.
Mm-hmm.
I haven't seen any kinematics or any like we did like one that pertained to
pure physics is like a very
electrostatics.
small portion of the test.
Really?
Yep. I did like the breakdown in that slideshow of like, what the questions are like.
Mm-hmm. I just want to find one that pertains to. This is all like chemistry and.
Mm-hmm. Yeah. Do you see my shared screen?
Oh no! Wait. Yeah.
Yeah. So I did the breakdown. So you should only really see like this many like whatever physics questions, like 15 maybe total.
But this is based on the section. What is this based on? Like the next step full length?
No, the actual test. Like biochemistry is 50% of the science section, 25% CP, 25% BB. Biology is 70%, 5% in CP, 65% in BB. Gen Chem is 35%, 30% in CP, 5% in BB. Orgo's 20% with 15% in CP, 5% in BB. Physics is 25% and only in CP. And 25% of 59 is 14.75.
That is even more hilarious, the fact that physics majors still do better, and the less content of physics, like the the least subject that's present on the test is physics, and they still do better.
Yeah.
Oh, wow. Well, I wanted to find some, but I guess it's fine. I'll keep working on this once I need to do something for work, and then
I threw a
keep
physics
working on
question
them.
here for you. In the latest thing in your notebook.
Oh yeah, I saw that. I was like, I thought that was someone, but we haven't done that, did we?
No. I wanted to like add like a physics problem like for you to do.
Okay.
But yeah, okay.
Can we?
I have to go now though.
Okay.
So, like I might I have like an appointment that ends at like 5:15. I'll like talk to you then.
Okay.
But
Just remember to if whenever you're done with your appointment, to copy the metabolism thing to the notes.
Oh yeah, okay.
And to make the request for it, because you always have to request through Zoho.
All right. Okay.
Okay.
Yeah.
Thank you.
All right. No problem.
Bye.
All right.